So now remember that we want our heap to function as a priority queue, and that specifically means that when it comes time to extract data from the priority queue, we need to grab the data that has the highest priority, right? And at a practical level, that means we're going to have to take the data that's in position 1 in the data array and effectively take that out of the heap, and also throw away the corresponding priority, which would be in position 1 of the priority array. But we have to be careful about all of this, just as we had to be careful with insertions. Exactly what are we going to do mechanically here to effectively do that? And and then how do we have to fix things up to make sure we still have a heap structure? Okay, well, so first of all, for reasons that we're going to see later when we talk about Heapsort, instead of actually removing data from the array and removing a priority from the priority array, we'll do this. We'll swap what's in position 1 with what's in position heap size. Okay, so think about this. The first move in this is going to be to interchange, to swap basically the first thing in the heap with the last thing in the heap. Okay? You might be thinking to yourself, what good does that do? That doesn't actually remove anything from the heap, but stand by here. So whatever's at the top of the heap in position 1 is going to get moved to position size, right? If we then decrement heap size, then even though what was at the top of the heap is still in the array, it's no longer part of the heap, right? Because the heap has shrunk. Okay? All right, you'll see this in an example pretty soon. So we've effectively taken the top of the heap out of the heap, and in its place we put the very last entry in the heap. Okay, the last node, if you like, has now moved to the top of the heap. And you might very well think to yourself, well, that sounds like a terrible idea, because whatever's at the bottom of the heap probably has a low priority, and you've just moved it to the top of the heap. Okay? Nevertheless, this is exactly what is done when one extracts the top of the heap from the heap. Okay? But then, of course, some work has to be done to patch things up, just as we had to do some work to patch things up when we inserted. Okay? Well, here, to patch things up after this removal, we follow a procedure known as heapify down. So I say again, as strange as it might sound, in order to remove what's at the top of the heap, what we're actually going to do is swap it with what's at the end of the heap, okay, as the first move. And then we decrement heap size. Okay, let's look at our example. So a moment ago we had left off with this heap containing 11 pieces of data, and so 11 corresponding priorities, and this is what our priority array looked like, right? So we swap the first and the last, okay, 57 gets promoted to the top of the heap, okay? We've swapped the last thing in the heap to become the first thing in the heap, and its priority is 57, right? Which is small. And again, it seems strange that we should want to do this, right? Whereas what we're trying to remove from the heap has priority 88, and we now see that priority at the end of the list of numbers, okay? And then after decrementing heap size, it's effectively as if the 88 is no longer there, right? Because now the heap only consists of 10 things, and so there are only 10 priorities. Only these first 10 numbers are considered to be priorities for things that are in the heap. So again, it's kind of a strange thing that we just did a swap that caused the data at the end of the heap, whose priority is actually pretty small, has been promoted to become the top of the heap. Okay? So we have to fix that. We have to use this heapify down procedure to correct things. Okay, at the moment, we've got a root whose priority is 57, right? The top of the heap now has priority 57. And that's no good because it has two child nodes that have higher priorities. Okay? If it even had just one child node with a higher priority, that would be bad, and we need to fix it up, right? But here we've actually got two child nodes, both of which have higher priority. All right, so here's how we have to patch things up locally. Among these three nodes, the node that has the highest priority is the left child. The left child has priority 82. Okay, so we do a swap. We swap the root node with its left child. And as we do that, the new root has priority 82. It has a left child with priority 57 and a right child with priority 72. So let's pause and see what things look like conceptually at this point. Right, so here's what the binary tree looks like now. Well, this is what it looks like before the swap. Here's what it looks like after the swap. The root, as I said, now has priority 82, and it has a left child whose priority is 57. Okay? But we're not quite done, of course, because as we compare the node with priority 57 to its child nodes, we see again there's a problem here because the priority rule is violated. Okay, node at position 2 has two child nodes at positions 4 and 5, and the node at position 5 has a higher priority than the node at position 2. So, as you guessed, we have to swap those two. Okay, and there it is. That's how things look after that swap, but we have to be careful. We now proceed to compare the node at position 5 with its child nodes. Well, there's in fact only one child of the node at position 5, namely the node at position 10. And we quickly see that things are okay here, right? The node at position 5 has priority 57. The node at position 10 has priority 55. So we don't need to swap those two, okay? And we have restored the heap. Okay, so this is a heap again. Priority rule is intact, and we quit. We're done heapifying down. Once again, may or may not bear repeating, but every time we do a swap in the priority array, we have to do a corresponding swap in the data array. This is just a quick look at how things would actually take place in the priority array. You can check this out on your own, right? This is what it looked like before we did the first swap. This is the result of doing the first swap. This is the result of doing the second swap, and the heap is now restored. Just to remind you that we actually have that number 88 in that position 11. It's still there, but it's not part of the heap. So I point that out because I want you to now think what would happen if we continue to extract from the top of the heap. Okay, so if we did another extraction, then the priority 82, which is currently the priority of the root, well, that would get swapped. That would get swapped into a position just before 88 in the array. Okay, and then after decrementing heap size, it would no longer be considered to be part of the heap, but it would still be in the array, right? So the two priorities here at the end, 82 and 88, while they're not, part of the heap, they're still part of the array. Okay, and that raises an interesting possibility. Let's see. Let's do another extraction. So now the priority 72, which is the priority of the root, will get swapped and put into the position just before 82. If we continue to extract from the top of the heap until the heap is empty, okay, well, these priority numbers will not disappear. They're still inside the array. Heap size will now be 0, so there's nothing in the heap. But all of these numbers, all of these original priorities, are still in the array, and you might notice something interesting about them, right? They're in order. They've been sorted. Okay? So you might be thinking, oh, gee, just what we need, another way to sort numbers. Okay, but I want to point out that we haven't just sorted these priority numbers. We've actually rearranged the data in the data array, right? Now the data in the data array could be any type of data. Could be student record objects, for example, right? Any kind of data that you're trying to keep track of. And because every time you do a swap in the priority array, you also do a corresponding swap in the data array, you'll have rearranged the data so as to sort it too according to increasing priorities. Okay? And that can be a useful thing to do. That technique is known as heap sort. And that's really all we're going to say about it. I guess I'll indicate just simply indicate that it has a time complexity like merge sort and quick sort, namely it is big O n log n. Okay, so the time has come to actually jump into the code for Heapsort, sorry, for Heaps and Heapsort that is posted at the course site. So again, invited to take a look at and run and really examine either the C++ or the Java version of this. We aren't going to have the time to go through all the details of this code, but let's take a fairly quick tour of it, and then again, I encourage you strongly to really get your nose into it and examine the code and check that it really does do the type of stuff that we just did visually and by way of examples. Okay, so there's a class called heap and heap size. Heap and heap size. Maybe that name, maybe that class should be more properly named heap. Okay, so an object from that class represents a heap, and there's code in it. There's code provided. There are methods provided to do all of the type of stuff I've been discussing. Okay, inserting into the heap. Extracting from the top of the heap, and finally performing heap sort. Okay? Now, just as I did with some previous code, let's see, linked list and the queues before that, I've arranged for this to work with numeric data. So you don't see any specification here of what the data type is for the data that's being maintained by the heap, right? Instead, down in the testing code that is actually going to construct a heap and heap sort object, the type of data will be specified down there. And you'll see, if you're going to run down and look at that real quick, you'll see that when we actually use this thing and construct a heap and heap sort object, we're gonna construct one for holding data of data type vehicle, right? If you look, there's a class in there called vehicle, and it's used to maintain information about different types of vehicles, and it's pretty simple and basic. This is implemented. Heap and heap sort is implemented exactly as I described earlier. I have two different arrays, two different actual arrays, one for the purpose of managing the data. In this example, will be again vehicle data, yes? And there's another integer array, and the integer array holds the priorities. So then there are some simple methods that help us navigate conceptually through the binary tree, right? If we know the index of a node, we can find the index position, in other words, of its left child. The position of a left child is 2 times the position of the parent node, and the position of a right child is 2 times the position of the parent node plus 1. If you forget that, go back and look, right? Remember I said if a node had position I and has a child, then that position will be 2i. If it has a right child, that position will be 2i plus 1. Okay, then there are methods whose names make it pretty obvious what their purpose is. There's a method called insertNode for inserting something new into the heap, and it bears examination. It really is worth your while to look at that code and observe there's a loop there that implements heapifying up. Okay? There's another method whose name is getTopOfHeap. This is for extracting whatever's at the top of the heap. And as we discussed, what it really does is it swaps that with something at the end of the heap, then it decrements the heap size, and then it performs the heapifying down operation. And again, you'll find a loop inside there, and you should look at that loop and convince yourself that it is correctly implementing the heapify down procedure. I've also provided some methods for the purpose of displaying the data that's inside the heap, right? A little technical point here. Since the testing code that I provided uses the data type that's maintained is data of type vehicle, if you check the code for vehicle, whenever there's occasion to display a vehicle, all it actually does is display the name of the vehicle. Okay, the other information is not displayed. Okay, that's not really of any significance here. It has nothing to do with heaps, right? But you might be interested in, I'll tell you what, I'm not going to stress this code as far as you studying it. I'd like you to run the program and see it in use so you can see the heap structure. But this display code allows you to actually visualize the binary tree. Okay, if you look carefully at the display, you'll see that the binary tree is displayed a level at a time. So each level is displayed on a single line. Okay, it's not a perfect rendering of things, but you can at least see the individual levels laid out. Okay, so as usual, take a careful look through everything. No kidding, take a look at the code and make an effort to make sense of it. And when you're ready, take the self-quiz.